All right, chemistry, this is your video lecture, part 2 of chapter 4, section 2, talking about the quantum model of the atom. In this half of the lecture, we are going to list the 4 quantum numbers and describe their significance, and then relate the number of sublevels corresponding to each of an atom's main energy levels, the number of orbitals per sublevel, and then the number of orbitals per main energy level. Now that seems like a lot of memorizing, but there will be a numerical system for you to remember that will help you deal with that particular objective. All right, let's move forward in the presentation to where we need to be. All right, atomic orbitals and quantum numbers. Quantum numbers specify the properties of an atomic orbital and the properties of electrons in those orbitals. So there are 4 atomic numbers that we are going to be dealing with, or there are in general. The principal quantum number, which is symbolized by a lowercase n, indicates the main energy level occupied by the electron. Then there's the angular momentum quantum number, symbolized by a lowercase l. It indicates the shape. All right, so we have the energy level, the main energy level, symbolized by n. We have the shape that orbital takes, represented by a lowercase l. Then we have the magnetic quantum number, symbolized by a lowercase m, indicates the orientation of an orbital around the nucleus. So we have the main energy level, we have the shape, and then the orientation of that shape. And then lastly, we have the spin quantum number that has only 2 values. It can either be positive half or negative half, which indicates the 2 fundamental spin states of an electron in an orbital. So let's take a look at this. You're going to read this diagram from left to right. We're going to start with the s orbital. The s orbital is the first orbital to be filled. The s orbital is spherically shaped. There is 1 s orbital for each value of n, 1, 2, and 3, and so on and so on. As we move to the right, we get to the p orbital. For each of the values of n, if n is 2 or 3 or 4, there are 3 p orbitals, and they're all dumbbell shaped, but they differ in orientation. Once we get all the way to the right, we see the d orbitals. And for each of the values n equals 3 or 4 or 5, there are 5 d orbitals. 4 of the 5 have pretty similar shapes but differ in orientation. And then there's this last d orbital that has this weird ring shape around the origin. This and the following couple of slides are going to be reference tables that you can use to get used to the pattern of numbers that occur with principal energy levels, sublevels, number of orbitals in a sublevel, and then the number of electrons possible in a sublevel. And you'll notice at the top here, we have certain equations that are going to help you calculate that instead of memorizing it. So you want to familiarize yourself with 2L plus 1, 2 multiplied by a 2L plus 1 quantity, and on and on and on. Familiarize yourself with that rule, not just memorization. And here's the continuation of that first table. We have principal energy level 5 and 6, the exact same type of information that we just saw, just with 2 more principal energy levels. Now we have the quantum numbers for the first 30 atomic orbitals. And here we see the pattern. You have when n equals 1, L can only equal 0, M has to equal 0. That orbital is 1s. When n equals 2, L can be either 0 or 1. If M is 0, then that's a 2s orbital. If M is -1, 0, or 1, that is a 2p orbital. And we'll see these patterns moving on and on and on. This is the fruition of the rules that we read about on the previous table.
All right, so let's talk about the atomic orbitals. So we originally had the idea that an atom looks like a nucleus in the middle, positively charged nucleus with the electrons orbiting around it. We're going to say we're not going to use that model anymore. It's extremely outdated. We're going to ignore it. It's great for simplistic ideas of how an atom behaves. But now we're going to talk about we're getting more into chemistry. And we're going to talk about more in-depth things. So we're going to now use the more updated model, which is a quantum mechanical model. So Schrödinger, along with Heisenberg, came up with a new idea of what an atom looks like. It's the one we use today. Heisenberg's uncertainty principle states that it's impossible to know precisely both the velocity and locations of an electron at the same time. And he, along with Schrödinger, he kind of like calculated this huge mathematical idea of where an electron can be found, came up with this new idea of what an atom looks like. So if we go over here, we're going to actually try and describe what it is and where an electron can be located within an atom. So if you have a nucleus in the middle, and here is here's the nucleus, and back here is where the electrons are located. There are different energy levels, the principal energy levels where electron can be found. So in the principal energy level, n equals 1, n tells us n is basically which principal energy level is which. We have one orbital. We're going to call it the s orbital. And let's give an idea of what the s orbital actually looks like. If we take this balloon, it's a spherical balloon. S orbitals are spherical in shape. In the middle, we have a nucleus, and surrounding it, we have the idea of where the electron can be found. So there's one orbital for every s in s orbitals. There's only one. Looks like this. So we're going to say 1. In the n equals 2 principal energy level, there is an s also, a little bit bigger sphere. And there's also p orbitals. Okay, p orbitals look slightly different. This is what a p orbital looks like. This is 1. Even though there's 2 balloons, this is 1 p orbital. The nucleus is kind of where the knots are, and the electrons can be found either here or here, and it looks like a dumbbell shape. There are actually 3 of these orbitals together, they come together to look like this complicated mess. So electrons can be found in anywhere the balloons are. So the nucleus is obviously in the center, and the electrons can be found here, and there are 3 of them put together to make this 3-dimensional shape. So in the n equals 2, we have 1 s orbital, and then we have 3 p orbitals. In the n equals 3, it also has s orbitals. It also has p orbitals, but it also has a d orbital. D orbitals look like flowers, a little more complicated. I didn't get a chance to make it in balloons because it's a little bit harder. But it looks like a clover. And so the nucleus is found here, and the electron can be found in any 4 of these places. Now, this is just one orbital. This is not 4 orbitals. This is just one orbital. So electron can be found here, 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 or here. So you can find there's 1 s orbital, 3 p orbitals, and 5 d orbitals. They can be oriented in different ways along the axis. The n equals 4 principal energy level. You have an s also. You have a p. Again, you have a d, and then you also have an f orbital. F orbitals are extremely complicated. Each orbital actually looks very different from each other. So I'm not even going to attempt to draw it because each one's a little bit crazy. But there's 1 s orbital. Oops, I'm sorry about that. 3 p orbitals, 5 d orbitals, and as you can guess, there are 7 f orbitals. And f is actually, for now, the highest energy orbital that you're going to find. There are theories that there are other orbitals within the principal energy level. However, we're not going to go there because it's just theoretical at this point. So as you can, if you were to put all these guys together, you'd get this insane mess-looking thing. The nucleus being here, the s orbital, the 1 s orbitals, the electron can be found within that, then the 3 p orbitals, then the s, and then so on and so forth. So it's a lot more complicated than the Bohr's model, which is just a nucleus in the middle and the electrons surrounding it. So this is basically the atomic orbitals.
All right, we'll finish up with a 1 check for understanding that refers to the quantum numbers. Which of the following is not described by the first 3 quantum numbers? That's principal, angular momentum, and magnetic. Which of the following is not described by one of those 3 quantum numbers? The correct answer is C, spin. Spin is its own quantum number. It's actually the 4th and last quantum number. All right, chemistry, that is going to do it for the lectures for this section. I will see you next period.